Okay. Hello, my name is Josef Haider, and I'm going to be talking about TruffleStrings today. I've been part of the Oracle Labs Graal VM team since 2018, and I'm the main author of TRegex, the Truffle regex engine, and now also TruffleStrings, a multi-language string implementation. First things first, why do we want to have a custom string implementation for Truffle languages? All Truffle languages are implemented in Java, so they all have access to the already highly optimized Java string implementation. But unfortunately, most programming languages leak almost all of their internal string implementation details to the user, which creates expectations about the behavior of that specific programming language's string implementation. So for example, in JavaScript, strings are encoded in UTF-16, just like in Java. And if you create a string from an emoji character, this character doesn't fit in a 16-bit value, and JavaScript will encode it internally as a surrogate pair, which is two 16-bit values, and it will report a string length of 2, and it will allow the user to access both of these values. Similarly, for example, if you do the same in Ruby, Ruby will internally encode the emoji character in UTF-8. It will report a byte size of 4, and it will grant the user access to each of these individual bytes. So language implementations really have to adhere to the encoding that the individual language originally chose. If you want to be able to run user code which was written for an arbitrary Ruby or Python or whatever implementation. So this is the first problem. Second problem is Truffle allows strings to flow from one language to another. So you could create a string in JavaScript. You could pass that to a Ruby function and return a Ruby string from there and pass that into a Python function. And all of these boundaries, all of these strings passing boundaries may have to be converted from one encoding to another. And traditionally, when passing this boundary, you would have to convert to Java string, and potentially in the language receiving the string, you would convert from Java string again into the language specific string implementation. For example, in Ruby, that would be the case. So what we want to have is we want to have one string implementation for all languages that use the Truffle framework. So we have the string implementation available in the Truffle framework, and that string implementation should be able to accommodate the use cases of all languages. It should be easy to convert between different encodings, between whatever individual languages expect from a string, and it should be fast and should basically be like Graal. So it should be able to do everything and still be fast, right? So just to give an overview of the different encodings used in programming languages currently implemented on Truffle, we have Espresso, which is Java, so it's got the same expectations as Java strings. JavaScript, fortunately, does the same. Node.js, on the other hand, uses UTF-8 internally a few times. Python uses UTF-32 with two-level string compaction. So this, for example, creates the expectation that you have constant time access to all code points, regardless how large they are. R uses any encoding. It just uses your system encoding. So encoding can be pretty much anything. Ruby also allows a user to choose a custom encoding for any string, and at least it defaults to UTF-8 and not your system encoding. So that's a little bit easier to handle. But just from these programming languages alone, we already need support for UTF-8, 16, and 32 to be able to handle all of these cases. Also, another benefit we want to get from our custom string implementation is we want to be able to share optimizations for all languages. We want to have lazy concatenation, lazy repetition, which is just a special case of concatenation. We want lazy conversion from int to string. We want easy conversion from TruffleString to JavaString and back. We want string views, so we want to be able to have substrings without copy. This is especially important for JavaScript because V8 does the same, and in some cases this can mean a speed difference of several orders of magnitude. We want to be able to have string views into native memory, so especially for languages that allow C extensions. This is, for example, important for Node.js and Python and also Ruby, because especially some modules will use strings that are backed by memory from the C data sections. Also, we need to have string compaction for UTF-16 and UTF-32 to adhere to the memory model used by Python and Java. Additionally, we decided to go a little bit beyond current optimizations already available and decided to also track the code range of a string. Code range in this setting means that we want to be able to tell what is the upper limit of code points present in a given string. And we categorize these in very coarse categories. So we want to be able, is a string consisting only of ASCII characters? Is it only Latin 1 characters, or is it only basic multilingual plain characters? The biggest benefit from this is that, for example, ASCII is equivalent in almost all encodings. So if you know that, for example, a UTF-8 string is ASCII only, and you want to convert it to UTF-16, normally you would hand it to the very expensive transcoding implementation, and that would go through every byte and do whatever it needs to do. But if you know it's already ASCII, you can pretend that your UTF-8 string is just an already compacted UTF-16 string and just use the same array. So that would give you a no-op string conversion for ASCII strings, which ASCII strings are very common, especially in a program, especially for identifiers and stuff like that in a programming language. So this can provide huge benefits when converting between individual encodings. Also, ASCII, Latin 1, and PMP strings, depending on the encoding, can also mean that if you want to access code points based on a code point index, your index are suddenly constant. Your accesses are suddenly constant time and no longer linear to the string length. Additional requirements introduced by Ruby, because Ruby has the most flexible string implementation, is that Ruby allows a user to mutate a string. You can overwrite individual bytes, which renders the string basically equivalent to a byte array. So we also have to be able to map that into TruffleString. And Ruby exposes the ASCII only code range to the user. So we actually have to track at least the ASCII code range for Ruby explicitly. So all of these requirements give us a pretty result in a very, very generic string implementation. We want to be able to support almost everything you could want from a string. We need to support almost all encodings that exist. So the current implementation supports around 100 encodings. We want to support string compaction. This is especially for UTF-32. So we want to be able to compact UTF-32 strings to 16-bit and 8-bit values if the code points are less than what you would need. We want to support native and managed backing storage for strings. We want to support immutable and mutable strings, and we want to support lazy and, of course, materialized strings. In the final implementation that is currently in Graal, I came up with the following data structure for TruffleString. We have a common base class for immutable and mutable strings, which contains this generic data pointer, which holds the string's contents. It can point either to a Java byte array, it can contain a native pointer wrapper, or some lazy data structure. So when you create a string by lazily concatenating two strings, you would create a new string that contains such a lazy data structure. And as soon as you want to access the string's internal byte array, you would replace this internal lazy structure with a materialized byte array. Additionally, we have offset and length properties for string views. We have the encoding and the compaction level, internal flags, a cached hash, just like in JavaString, the cached code point length, which is especially important for Ruby, and the code range, which we already talked about. Additionally, we have a transcoding cache in the immutable string. So when you convert a given string to another encoding, TruffleString will cache the transcoded version in an internal cache ring structure. So the next time you convert the same string to the same encoding, TruffleString will look that up in the internal cache and give you that instead. The amount of operations exposed by TruffleStrings are too many to cover right now. So we expose all of these operations as truffle nodes to be used by truffle language implementers. And almost every single operation has one variant where indices are byte-based and one variant where indices are code point-based. A few operations are specific to UTF-16 and UTF-32. And some operations are also instance methods of TruffleString, but everything that's more than just a little, than just a simple field lookup is typically a truffle node. Since on this conference we are more interested in the Graal compiler than in Truffle, I'll not go into detail on all of these operations, but focus more on the Graal optimizations we did specifically for TruffleString. So the most important thing when optimizing strings is to try to SIMDify everything. Strings benefit from SIMD immensely because they typically are just byte arrays. So when you, for example, SIMDify a floating point operation, you can do parallel processing on 8 single precision floating point values or 4 double precision values. On the other hand, when you are dealing with 8-bit string values, you can process 32 at the same time on an AVX2 YMM vector. So the speedups are, the potential speedups are a lot higher. For example, a very often used intrinsic is the one for array region equals, which just checks if portions of 2 strings are equal. The core loop on the left can be intrinsified and vectorized in just 3 vector instructions. So you just need one move, you need an XOR and a logical test, and that's it. These 3 instructions basically cover 32 iterations of the loop on the left. So we want to do this as much as possible for every single operation, if at all possible. How do we do this? We do this in a very similar way, or actually in the almost exact same way we did this already for JavaString and for things like system array copy or arrays equals, Java util arrays, that is, and stuff like that. We're using stub calls. Stub calls are calls to pre-written, handwritten assembly functions where Graal knows exactly which registers are used by the function, and therefore the call overhead is a little less. And during execution of these functions, we don't have to care about anything in the JVM. There are no save points. There are no restrictions we just run pure assembly during these function calls, during these stub executions. Let's go over some of those. Specific to TruffleString operations, we want to be able to use the same stubs for managed memory and for native memory. And we also have to take into account the string compaction level, especially for UTF-32 and UTF-16. So the Java signature for most intrinsics used in TruffleString have for every array parameter a byte array parameter and a long offset parameter. And if you want to use the intrinsic on a Java byte array, you just pass it as the array parameter and that's it. If you want to use it as with a native pointer, you just pass the native pointer as the offset parameter and set the array parameter to null. And the stub will just add the two together and use that as a base pointer. This is only okay in those stub calls, but since we don't have to care about the Java memory model, we can do this. Additionally, this is not yet merged, but I'll merge that soon. We also have a dynamic stride or string compaction parameter, which dispatches the stub into separate versions of the same stub for every compaction level or stride. So in this case, you could have 3 different values for the stride: 0 for byte stride, 1 for char stride, and 2 for int stride, 8-bit, 16-bit, 32-bit. And internally in the stub implementation, this would then go into a jump table, which would dispatch to the correct stub version. This is pretty cheap and allows us to get pretty good performance even without profiling the exact strides for individual TruffleString operation invocations. So I'm just going to go over the most important intrinsics we're using right now. First one is just generic array copy, inflate, and deflate operations. These are already present in the JVM for JavaString. I just had to slightly generalize them for TruffleStrings, especially for UTF-32. So we now no longer have only 8-bit and 16-bit inflate and deflate, but also 32-bit variants. These are extremely simple. You can do this by just using zero extending moves and pack operations. Same thing for array equals and region equals, which I already mentioned. Since this intrinsic is used pretty often and is pretty important, I also added a special version for cases where we know the exact length. So if the length is constant, we'll emit specialized assembly for those, because in many cases the string is short enough that we can get away with doing just 2 vector loads, one from the beginning of the string and one from the end of the string, and then doing the comparison in 5 instructions, which is a lot better than the scalar loop, of course. Next up would be indexOf int, so indexOf single value. This is also present in the JVM for JavaString already. We also had to generalize it a little bit. One thing that I changed here is that the previous implementation used pcomp-s3, which is an older x86 instruction, which was made specifically for string processing, but it's extremely complicated and it's not using the full vector length on more modern AVX2 machines. So I replaced that with simpler instructions, which boil down to comparison for equality, the p-test instruction, and the p-move mask instruction. So if we want to vectorize the loop on the left, what we have to do is just check the bytes for equality. Equal bytes will become all ones and the rest will become all zeros. And we can then convert this this mask, this vector mask, basically to a bit mask with the pmove mask instruction, and then determine the position of the match using a bit scan. So this is basically Java's count leading zeros. Same thing goes for index of substring. There we added another version that doesn't just check for one character, but 2 consecutive characters to find the beginning of a substring. And the rest of the substring is then checked with the already mentioned region equals intrinsic. So in the end, the index of substring operation uses these 2 intrinsics in a loop. Next up is the compareTo, which is also already present in the JVM specific Java string compareTo intrinsic, which was also using pcomp S3, which I also converted to more modern instructions. And just in case you're curious, I measured the impact of this a little bit. And in the results of these micro benchmark measurements, you can see pretty easily that as soon as you go over XMM vector size, the newer instructions are a lot better than the pcomp S3 version. So just to make clear, the x-axis is number of scalar loop iterations. So and we're measuring byte stride here. And lastly, we introduced one completely new intrinsic for TruffleString, and that is one that is the calculate string attributes intrinsic. This one does three things at the same time. Basically, it validates the string if it is encoded correctly. It calculates the number of code points in the string, and it also calculates the code range. This intrinsic is now available for US ASCII, Latin 1, UTF-8, 16, and 32. Simplest one and the base case for all encodings is to check if the string is ASCII only. This is always the same, and it's the most common case. This can be done with a single instruction. We just need to do a logical test on the string contents, where with a mask where the lowest 7-bit are 0 and everything else is 1. If this test results in a 0, we know that the string is ASCII only. This is extremely fast and scales almost perfectly with the vector length. For the UTF-32 variant of this intrinsic, we do basically only this p-test test for the string contents. And if one of the tests fails, we just have to gradually loosen the mask to the next code range. So we first check if the string is ASCII only, but if that fails, we loosen it to Latin 1, and if that fails, we loosen to a basic multilingual plain. The first case where it gets a little more complicated is UTF-16. So if we find that the string is not ASCII or Latin only, we also want to check if the string is encoded correctly. And for that, we need to check surrogate pairs. I'm running out of time, so I'll have to go over this a little faster. Basically, what we do is we identify leading and trailing surrogate values, also with pcomp equals, and then XOR them together. If the result of this XOR is 0, the string is valid. So this also scales pretty well with the SIMD intrinsic. And for the most complex case, UTF-8, I just ported an already available algorithm from the extremely excellent paper validating UTF-8 in less than 1 instruction per byte by John Kaiser and David Lemire. I ported that publicly available algorithm into Graal. So this is available now in Graal Community Edition, and this algorithm is able to validate UTF-8 strings in one branchless loop, which is extremely impressive. And I won't be able to explain how it works in this talk, but the core of the algorithm is a vectorized table lookup, which is done via pshaft-b. I'll have to gloss over this because I'm running out of time, sorry. Just very quickly, since most strings are very short, we often run into the problem that a string is maybe just only one vector length long or even less. So what we do to combat this is we do overlapping vector loads, just one from the beginning of the string, one from the end of the string. And in most cases, we can actually do that without any penalty, even if we are processing elements of the string twice. In case where we have to take care to not process elements twice, but if 0 elements don't change the result, we can still do this with a constant mask from memory by zeroing out duplicate elements. And if these 0 elements still causes problems, if they're in the middle of the vector, so to say, we can even then still do this trick by moving them to the left with already pre-existing pshaft-b mask in memory. So what's the impact of all of these intrinsics? I just did a lot of micro benchmarks for those, measuring the speed up we get from running these operations as just in the scalar form versus the vectorized intrinsic. And in pretty much all of these benchmark results, you see the speed up starts happening starting at 8 bytes. So, and since all of these operations are super simple, the speed ups are almost the same as your typical vector size. So the result looks pretty similar on all of our intrinsics, even on the UTF-8 validation intrinsic, which is pretty impressive. For UTF-16, the validation is a little slower because in this case, of course, we're not running on a byte array, but a char array, basically. And I realized that all of this is specific for EMD64, what I talked about so far, but we are also planning on porting all of this to AR64 using Neon and scalable vector instructions. We already have ported versions of most of these, and we're just missing a few customizations for TruffleString. So these intrinsics are not enabled on AR64 yet, but are soon to be. So that's it for my talk. I'm sorry for taking so long. I wasn't sure what's most important here. It's merged already. Not completely everything I talked about in this talk, but almost all of it is already merged, and GraalJS is migrated already. Truffle Ruby and Graal Python are migrating right now. So if you want to check it out, it's available right now. Thanks.
Great. Thank you, Joseph. That was a very interesting talk. In fact, you answered my question that I put on chat. I was wondering what it would take to port all this to a different architecture, but it's good to see that it's in progress. Any other questions from the audience? I know we're a little bit over time, but we may have time for 1 or 2 questions. No, nothing.
Okay, thank you.
Okay, then thank you, Joseph. We'll catch up with you. Oh, yeah, Chris said it's great work. Agree.